Merhaba arkadaşlar, hoş geldiniz. Bugünkü dersimiz Chapter 5. Chapter 5 Series Solutions of Second Order Linear Equations. Okay. Well, let me say a couple things about why we, need to study series solutions. The reason is that most of the actually equations we have solved so far had solutions which can be expressed in terms of combinations of elementary functions such as sine, cosine, logarithms, and so on. But actually, if we write down a general second order linear equation which is not constant coefficient, its solutions most probably won't be written as a combination of these elementary functions. The only way you may represent the solution is usually to write down its power series expansion. Therefore, if you want to study real world problems which are not constant coefficient equations, then the solutions will have only power series expansions to work with. You may not write down solutions in terms of elementary functions. That's why we need to study power series solutions. Okay, so let me say this basically. Unless it is a constant coefficient equation, the solution of an linear equation, linear ordinary differential equation is most probably not written as a combination of elementary functions. Such as polynomials, rational functions, exponentials, logarithms, and trigonometric functions. So that's why we have to, study series solutions of differential equations. So what's a series? Maybe I should tell you what a series is. Okay, a power series is a formal sum of the form. So something like this: an x minus x0 to the power n, and from 0 to infinity, where x0 and an's are real or complex numbers more generally, and x is an indeterminate. Okay, so it's a variable. I guess you remember from calculus or real analysis course that if you let L to be the lim sup of an plus 1 over an, then R, which is defined to be basically 1 over L. So what is this? This is 1 over L if L is a real number. It is 0 if L is infinite, right? Lim sup might be infinite. Or it is infinite if L is 0. So R is defined this way. Then this number is called the radius of convergence. Convergence of the power series. Okay. And we have a well-known result which tells us when the power series is convergent in terms of the radius of convergence. So assume the above setup. Okay. Now, if x minus x0 is less than r, x being real or complex number, then the power series this power series converges absolutely. So it is convergent, but actually it is more than convergent, meaning that if you take norms of the terms of the series, this is convergent. So absolute values, or in case they are complex numbers, norms of these complex numbers added up converges yeah, if it is convergent, then we say that the series is converges absolutely. And of course, if it converges absolutely, then it is convergent. All right. The second part of the theorem is the following. If x minus x0 is larger than r, then the series uh, then this series is divergent. And in case it's equal to r, then no conclusion. It means it may or may not convergent. Okay, it may or may not converge. Sometimes it converges, sometimes it doesn't. So let's do one example. Okay. Determine the radius of convergence and the interval of convergence of the following series. Okay, what are these? This geometric series, and then okay, look at this one, and from 1 to infinity, c is x to the power n over n factorial. This is the exponential function, right? And okay, n factorial times x to the power n, and e is 0 to infinity minus 1 to the power n x to the power 2n. Sorry. Yeah. Okay. Solution. Let's start with the first one. So our series is this. Okay, if I compare this with the general form, then we see that x0 is 0 and an is just 1, right, for all n. So what is the radius of convergence? Well, L is just lim sup of an plus 1 over an. Well, in this case, they're all 1, so this is just lim sup of 1. Well, of course, this is 1. So R is just 1 over L, which is 1. So the radius of convergence is 1. And this means what? If I draw the interval about 0 of radius 1, so this is 1 and this is minus 1, then I know that at an insight point the series is convergent and it is divergent here and divergent here, and at the boundary points, sorry, this one and this one, 1 and minus 1, we don't know. The theorem doesn't say anything. We just need to check. So let's do that to find the interval of convergence endpoints. We have two endpoints, minus 1 and 1. So at minus 1, we have what? So I plug it here, minus 1 to the power n. Of course, this is divergent. Divergent, since the general term of the series, this limit is not equal to 0. If it were convergent, then this limit would be 0. Okay, what about x equals 1? Well, the same thing basically, right? 1 to the power n. So this is clearly is divergent since limit. Well, if you add once, then you get infinite, right? So this is divergent. So endpoints, at the endpoints, the series is not convergent. Hence, the radius of convergence is not the radius, the interval of convergence. Interval of convergence is minus 1, 1, right? All right. Part B. X to the power n over n, and from 1 to infinity. So if I compare this with the general form, we see that x0 is 0 again, and an is just 1 over n. A0 is 0, and others are just 1 over n. Okay. So what is L then? Lim sup of an plus 1 over an. Well, this is lim sup of 1 over n plus 1 over 1 over n. Well, this is just n over n plus 1, and its limit is just 1, right? So again, r is just 1 over l, which is 1. So the radius of convergence is again 1. Okay. So it is again convergent inside, divergent outside, and we need to check the endpoints. Okay, let's do that. Endpoints are minus 1 and 1 again. So x equals minus 1. Well, this gives me what? So minus 1 to the power n over n. Well, this is convergent by the alternating series test. What is that test? That test is this. So given a sequence an with the following properties. One, an's are all non-negative. Second, an is decreasing. And third, limit an is 0. Then this series, so if you add up these numbers alternatingly like this, then this is convergent. What about the other endpoint? So it is the series 1 over n. This is divergent right? It is the harmonic series. Okay, so what is the radius of interval of convergence? Hence, the interval of convergence is minus 1 is included, but 1 is not. All right, so it is this one. C was the, I guess, exponential function. Yes. So x to the power n over n factorial. So if I compare this again with the general form, again x0 is 0 and an is just 1 over n factorial. So L, which is lim sup of an plus 1 over an, well, if you plug this, so you will get 1 over n plus 1 factorial divided by 1 over n factorial. This is just limit of 1 over n, and that is 0. So L is 1 over 0 basically, so it is infinite. Okay. So this means, hence, the series converges absolutely, of course, for all x, real or complex numbers. Okay. But actually we know that this thing is something we already, we are familiar with. This power series is nothing but the Taylor expansion of the exponential function, right? Here actually we had something similar. So here, yeah, okay. Okay, I'll do it later, I guess. Yeah, okay. So let me do D. D is so in this case x0 is again 0 and an is just n factorial, and if you combine L, lim sup of an plus 1 over an, so n plus 1 factorial over n factorial, that is n plus 1 and its limit is infinite, and therefore the radius of convergence is 0. So it means, hence, the series is convergent only for x equals 0. When I plug x equals 0, I just get 0, right? Yes, maybe just the first term, it is 1, and it is convergent. Besides that, it won't be convergent. So only for x equals 0. And I have this. Okay, there is. Well, okay, let me regard this as t to the power n, and from 0 to infinity, where t is minus x squared. Okay, minus x squared. Well, we know that this is convergent. We know that this is convergent only for t less than 1, right? Therefore, so t is less than 1. Of course, if and only if minus x squared is less than 1. And this is if and only if x is less than 1. Therefore, again, this is convergent. Radius of convergence is still 1. Okay, still 1. What about the endpoints? Okay. Well, actually, we know this, right? This is the geometric series, and this is nothing but 1 minus t, right? For t less than 1. And if I plug minus x squared, so we see what? 1 plus x squared is equal to, so minus 1 to the power n x to the power 2n. And this is true for, again, x less than 1 in absolute value. All right. Well, let's look at these two formulas. Here we understand that we cannot plug t equals 1, right? When you plug t equals 1, the right hand side explodes, and the equality, will give us nothing. It's just infinite equals infinite. However, if I look at the second equation, here I can plug x equals 1, right? There is no reason why I can't plug x equals 1. However, if you plug x equals 1 here, then of course this is divergent. So this equation is not true if x equals 1 or minus 1. And it is not clear, uh, uh, as this one, because here you can't really plug t equals 1. However, if you think complex numbers, actually the picture is more clear. Why is that? So if x is a complex number, then this is convergent for x equals, for x less than or equal to 1 in absolute value. Radius of convergence is 1. Well, if you draw the ball with radius 1, then you have I here, and minus I here, and minus 1 here. And you see that you cannot plug I or minus I into the right hand side, right? Because it makes the denominator 0. So we have a situation similar to this one. Therefore, actually, it is more natural to consider power series as a complex power series, okay? Then you understand better, what's going on. Okay. All right. Maybe a couple things about power series also. Okay, now suppose that uh, an x to the power n has radius of convergence r greater than or equal to 0, greater than 0. Then of course f from r, well, not r, okay, x0 minus uh, r x0 plus r into r, or you may consider, complex variable. Here you write the ball with center x0 and radius r, and here you write c. Then this is a well-defined function. Okay, what's the function given by this series? Okay, uh, is a well-defined function. Moreover, we know from calculus that we can compute derivatives and integral of this function term-wise. Namely, okay, f is just this power series, right? So it is just a0 plus a1x plus a2, sorry, a0, a1 x minus x0, a2 x minus x0 squared, and so on, an x minus x0 to the power n, and so on. And we know from advanced calculus or analysis courses that, okay, 0 an x minus x0 to the power n, so a0 plus a1 and so on. What is the derivative? Derivative is this. You just take derivative of each term, so this is just n times an x minus x0 to the power n minus 1. So if I take derivative here, a0 will give me 0, of course. I will have only a1 here, and then 2a2 x minus x0, and then 3a3 x minus x0 squared, and it will go like this, n times an x minus x0 to the power n minus 1, and so on. And what about the second derivative? Well, that will be n times n minus 1 times an x minus x0 to the power n minus 2. Alright, so it will be 2a2 and 6 a3 x minus x0, and here n times n minus 1 x minus x0 to the power n minus 2, and so on. Okay, the observation is this, so this will continue like this. The observation is that if I plug x0 in f, now all these terms vanish except the first term, so the result is just a0. If I plug x0 in the derivative, again all these terms will be 0 except the first one, so it will be just a1. And similarly, the second derivative, it will be 2a2, but let's write it as just 2 factorial times a2. And then if you compute third derivative, so you will take derivative one more time, so it is just 6a3, but that is nothing but 3 factorial a3. And you see immediately that actually this generalizes, and nth derivative is just n factorial times an. Because you have this term, you take derivative over and over. Each time this exponent comes down. First I had n, and then n minus 1, and then n minus 2, and so on. So if you go up to n, you will have n minus 1, and then n minus 1. So it will be 2 and 1. So you will have just n factorial. Okay, so n factorial times an. And from this, we see what? Hence, if we have a convergent power series about some point x0, then the coefficient an is just the nth derivative of the function evaluated at x0 divided by n factorial. Alright, so this is true for all n. Okay, well, why this is important? Corollary of this is the following, or maybe let me write this way. Suppose we have uh, two power series uh, okay, with this property. So an x minus x0 to the power n is equal to bn x to the power x minus x0 to the power n. Okay, and suppose that they have both the same radius of they have both positive radius of convergence. Well, okay, this is true for all x in some, such that for all x with, okay, so on some ball like this. Okay, then we have what? Well, this power series which are equal on this ball defines a function, and by the above argument we know that this an is just nth derivative evaluated at x0 divided by n factorial, but that's also equal to this power series, so bn can be computed the same way. Therefore, an and bn are the same. Okay. This implies also the following. So if we have a power series, and if this power series is equal to 0 for all x in some open set, okay, let's say x minus x0 less than r for some x0 and r, then, well, I may regard 0 as a power series, right, where all the coefficients are 0. And by the above argument, these coefficients must be the same, so all an's must be 0. Then an must be 0 for all n. Okay, 0, 1, 2, and so on. Okay, this will be something crucial. Okay, now let's pass to the other sections. So I will cover section 5 over 5.2 and 5.3 simultaneously. So these are just series solutions near an ordinary point part 1 and part 2. Okay. Well, here we will consider second order homogeneous linear differential equations, but it won't be a constant coefficient equation because we have already studied those. This is this will have variable uh, coefficient functions. Okay, so consider a second order uh, linear ordinary differential equation of the form. So it will be also homogeneous. Homogeneous. So this is the form px times y double prime, some other function times y prime, and rx y equals 0, where p, q, and r are uh, analytic functions. Okay, on some about some uh, point, say x0. So analytic means these functions have power series expansion about x0 with positive uh, radius. So px is something like this: pn x minus x0 to the power n, and from 0 to infinity, and qx is just qn times x minus x0 to the power n, and rx is just rn x minus x0 to the power n. Okay, so and they may have different radius of convergence, but we assume that they are all positive. Okay, we will say that the point x0 is an ordinary point for the equation if what happens if the leading coefficient function is not 0 at x0. Okay, this of course means the following: then star can be written about x0 as like this. So y double prime plus qx over px, y prime plus rx over px, y equals 0. Okay, because px is not 0, therefore I can divide by px, and zeros of an analytic function are isolated. Therefore, there is at least some open ball in which these coefficient functions are, well defined. Okay, let me give an example of such an equation. This is called Aries equation. Okay. And it is this one. Y double prime minus x times y prime equals 0 for x is real variable here. So y is a function of x and x is a real variable. Okay. Here, what is px? Px is just the constant function 1. Qx is the constant function 0. There is no y prime term. And Rx is the polynomial minus x. These are all, of course, analytic functions, right? They are convergent power series. And the radius of convergence of each of them is infinite. Okay, so which are all analytic functions. And px is constant 1, so it is never 0. Since px is the constant function 1, and this is not 0, right, for all x, any x in R is an ordinary point. For the Aries equation. All right. We will come back to this equation later, but first let us state the main theorem. Okay. So if x0 is an ordinary point of the equation, which equation? So px y double prime, okay, plus qx y prime plus rx y equals 0, then the general, then the equation as general solution of the form. We know that it has a general solution because coefficient functions are continuous and they are well defined about some open ball, in an open ball about x0. So there is a general solution of the form, but the content of the theorem is the following. This general solution is given in has a power series expansion, and this power series actually breaks up into two pieces. Okay, where a0 and a1 are arbitrary constants and y1x and y2x are linearly independent series solutions that are analytic. Okay, analytic at x0. So y1 and y2 are also power series expansions. They are power series, convergent power series. They have positive radius of convergence. And actually the radius of convergence of this yi's is like this. Moreover, so the rest of the theorem is about that radius. Moreover, the radius of convergence of each yix is at least the radius of convergence uh, of the functions, analytic functions, qx over px and rx over px, right? The ratio of two analytic functions is also analytic, provided that the one in the denominator doesn't vanish at x0, and therefore these analytic functions have radius of convergence. We compute those radiuses and we take their minimum, and the theorem tells us that the solutions y1 and y2, the linearly independent solutions of this equation, have radius of convergence at least that minimum. Okay. Okay, let's give a break now.